This topic is optimization. To optimize something means to maximize or minimize some aspect of it. What is the greatest volume of a box? What is the least amount of material used in a can? What amount of medicine will maximize the body's sensitivity to that medicine? Or what amount of materials will minimize the cost? Now, because we are maximizing and minimizing, we will be finding local maxima and minima of functions. And then to actually answer the question, we'll probably have to find the actual function value at that maxima or minima. Now, the hardest part of optimization is coming up with a model for the variable that you want to optimize. Other than that, it's just the first derivative analysis. An open top box is to be made by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin and bending up the sides. How large should the squares be to make the box hold as much as possible? Or in other words, what is the resulting maximum volume? We're solving for both the x that maximizes the volume as well as the maximum volume. So here is our sheet of tin, 25 by 20. We're going to cut out some corner with side lengths both equal to x from all four sides of this sheet. When in doubt, make a picture. And right now we're making a picture to try to formulate some sort of model for the volume of this box. Now the volume of a box is given by the height times the length times the width. Now imagine the 3D model of this box. The height is x. The length is 25 minus 2x, because we're taking off both of those corners. And the width is 20 minus 2x, because we're taking off 2x's from the 20 side. This is the volume of our box in terms of one variable x. Now all we have to do is just multiply this out. We have 25x minus 2x squared, and we still have a 20 minus 2x. We can now distribute this even further. V of x is equal to 25x times 20 is 500x. 25x times negative 2x is negative 50x squared. Negative 2x squared times 20 is negative 40x squared. And negative 2x squared times negative 2x is positive 4x cubed. This is our model right here. The volume in terms of that side length x that we're going to be cutting off is given by 4x cubed minus 90x squared plus 500x. Now, in order to find the critical points of this and therefore possibly find the extrema, it is necessary to take the derivative and set it equal to 0. V prime of x is equal to 12x squared minus 180x plus 500. This always exists, so there's nowhere where the derivative is not existent, so we'll set it equal to 0 to see where we have horizontal tangent lines. These are possible extrema. We can first factor out the, let's see, we can factor out 2 from this. I'm not sure what else goes higher. We're left with 6x squared minus 90x plus 250. And that's all equal to 0. And now from this, we can probably factor out yet another 2. So we could have factored 4 from the very beginning, but whatever. So minus 45x plus 125, and that's all equal to 0. Now this quadratic doesn't factor very well, at least, and so let's use the quadratic formula to solve it. Here we have negative b plus or minus the square root. Negative 45 quantity squared, I believe, is 2025 minus 4 times 3 times 125. That gives us 1,500, and that's all over 2a. 2 times 3 is 6. This is nasty, granted, and usually these problems tend to be rather nasty. These usually come on the calculator section of the AP, and if they are not on the calculator section of the AP, then they're pretty simple to do. Now we can take 25 out of 525. That goes in about 21 times, so here we have 45 plus or minus the square root of 5 root 21 all over 6. These are my critical points. And of course, we can actually just approximate this on a calculator to approximately 3.68. That's our first solution of the quadratic, and our second solution is approximately 11.32. Now let's look back at the initial problem, because our domain is restricted here. First of all, x can't be negative. We can't cut off a negative length. That doesn't make sense. Second of all, 20 seems to be our smallest length, and if we cut that length in half, x would be 10, and the other side, x would be 10. If x were more than 10, then we would be cutting off more than the actual width there. So that means that x has to be between 0 and 10. That restricts our domain. We have to think about the initial problem and the real-life construct that restricts our domain. 11.32, that's bigger than our domain. That's more than 10. Therefore, that's out. So our only possible extrema is 3.68. Now, it would be wise at this point to do a line analysis to ensure that this actually is a max. But since it's the only extrema that we got, we can probably guarantee that this is going to work. However, in the future, it would be wise to do your line analysis to double check. Now let's find the volume of 3.68. We can plug it back into our volume function, x times 25 minus 2x times 20 minus 2x, and that's approximately 820.53. And that is the maximum volume of this box. Here is a graph of v of x from 0 to 10 on the x-axis and from 0 to 1,000 on the y-axis. On my calculator, I actually found the maximum right there of this function. Turns out it is at x equals 3.68 and y equals 820.53, which is my volume. So just looking at the function itself, v, it is pretty apparent that there is a global max as well as a relative max at x equals 3.68.